Okay, electric field due to an infinite charged wire. We would like to compute the electric field generated by the uniform charge distribution over a straight wire that is long, infinitely long, and the electric field at some field point with some radius, planar radius rho, is a perpendicular distance from the wire. What is the electric field? If I want to find the electric field, then what I have to do is a minus the gradient of potential. Then what is a V? In the calculation of V, we encounter this kind of integral. Let us prove this integral table. First, the sine hyperbolic of x is defined by the difference of exponential x and exponential minus x and divided by 2. Okay, if we set t equals sine hyperbolic of x and y equals e to the x, and here this is 1/2 y minus 1 over y as is written in here. Okay, sine hyperbolic x is replaced with t. Now we find this is a quadratic equation with respect to y. How? I multiply y both sides and multiply 2 both sides. Then I can reach this quadratic equation. The solution of this quadratic equation is this. Sure, there are two solutions. However, I have discarded this solution. You know the magnitude, absolute value of t is always less than the square root 1 plus t squared. So it is a negative. However, our substitution that y equals exponential x indicates that exponential can never hit 0. So this y must be positive definite. Because it is positive, the solution of unphysical solution, this guy has been discarded. Therefore, we have a unique value for y. Because we have thrown away this unphysical one, there is a one-to-one correspondence between t and y. Therefore, the inverse function is always defined. The exponential function has an inverse. This y has an inverse using this relation. T equals sine hyperbolic x. So x equals sine hyperbolic inverse of t. So this is the carbon copy. Just like exponential x equals y, then x equals log y, something like that. All right, so inverse hyperbolic function is log t plus square root 1 plus t squared. This is what we know. Why don't we take the derivative? If I take the derivative, y, with respect to x, because y equals exponential function, and we know the derivative of exponential function is itself. Therefore, it is y. So we make a separation of variable. That means make y on a single side. So, and we multiply dx over y both sides. Then what I get is on the right side, this is dx. On the left side is dx cancel. dy over y. Okay, this one, I can simplify this into this form. Okay, because y is t plus y is t plus the square root 1 plus the t squared. This substitution. Derivative dt d1 plus the square root of t, this guy can be expressed as a chain, if we can make use of chain rule, 2 square root and take the derivative of the argument. Okay, so it becomes a 2t dt and 2 cancel, so we end up with this expression. So this one is in here, and this dt, this guy, this one is dt. We can factor this dt out. Finally, what we obtain is this. So as a result, this integral is inverse sine hyperbolic function. By the way, if we make use of the fact that derivative of this is just an integrand, we will find that this calculation doesn't have to be necessary. Okay, let us solve the problem explicitly. We have the origin and the y-axis. There's a uniform charge distribution, and uniform charge distribution, charge divided by length. This is uniform. We have a source point Q. Source is always expressed as a prime, and because it's restricted along the z-axis, x prime is z times e to this unit vector along the z-axis. The potential depends on the distance of source charge and the field point. We use the field point whose coordinate is x. We introduce the perpendicular distance rho, and a fixed rho will give a circle. And here E rho hat is the unit vector along the planar radial direction that is expressed in terms of E1 and E2 with cosine and sine. Using Cartesian coordinates, rho is a square root of x squared plus y squared. We would like to collect the electrostatic potential and integrate it over the length minus 1/2 of L to plus 1/2 of L. And later we will increase the parameter L to the infinity to find the electric field produced by infinite wire. Sure, the azimuthal angle runs from 0 to 2 pi. What is the vector from the source to field? This is field point. Source is at here. So source to field point. That means the field subtracted by source. Where is the field? Rho, E rho, and Z E3. That is the point at which the charge is distributed. What is the magnitude? You know, E rho and E3, they are perpendicular to each other. Therefore, the magnitude of this vector is trivial. This is rho, this is Z, so this one, the magnitude is Z squared plus rho squared. Okay, everything is ready. What is the differential potential due to this small element of distance dz along the wire? We know the charge dq is the uniform charge density multiplied by the length Okay, and electrostatic potential is a charge divided by the distance, and over a factor is 1 over 4 pi epsilon 0. We pull this out and we find that this is the magnitude of R. Therefore, we are interested in evaluating this one. This is not mathematics. Everything has its own dimensions, so it is convenient to choose a dimensionless variable from in which the physical dimensions cancel. So I'd like to convert this differential form as a function of a dimensionless variable, and we know z runs from minus 1/2 of L to plus 1/2 of L. And we divide this one by planar radius rho, and this is the range of this dimensionless parameter. This is a pure number. So this is a physics. Now it becomes a mathematical problem. And we are familiar with this. We have already derived the integral table in here. However, this complicated integral table is in fact not necessary. Let me show you why. Potential is expressed as the integral. What I need to do is just to do the integral. So I could have used the integral table I obtained previously on the first page. However, I'd like to take the derivative of this because what I'm interested in is not the integral table, but the electric field. So electric field can be obtained by taking the derivative. But fortunately, we have a rho dependence only, and we have no phi dependence or z dependence. So we have no phi dependence. So the gradient has only a single direction. That means as rho increases, the strength of the electric field changes. So simplest way to compute this gradient is you could have made use of a XYZ component, but it has a rotational symmetry about this axis. So we would rather use a cylindrical coordinates. In that case, the gradient whose function depends only on rho is in this form. That it is just like that we have chosen a single direction only. All right, in this expression, what we find is I need to take the derivative with respect to rho. However, my function is this that is integrated out, and rho dependence appears in the upper and lower limit. Aha! If this is, we can make use of previous result on ESA7. So using that way, I can make use of the fact. But before doing further, I can simplify this integral. You know, this is an even function. Even function integral in the range from minus a to plus a is negative part and positive part, they are the same. So I have factor of 2, and I don't have to integrate over the negative part, and just copy the positive part only and multiply by 2. And then our problem reduces into this form. Now I can make use of the chain rule, and I know the derivative of integral is integrand itself. So I have the integrand as a copy of this. However, I need to find the chain rule. I need to take the derivative of the upper limit with respect to rho. That is L over 2 rho derivative. So the answer is this. Now everything is ready. I can replace this t with the physical values. T is a pure number. T is nothing but the Z over rho. Substituting Z over rho, and this is a Z is at upper limit is 1/2 of L. So Z over rho, that is L over 2 rho. So I can absorb this factor inside the square root, and I have a negative sign and this. Now I can find we have a 1 over rho dependence, and the negative sign cancels this negative sign coming from the minus gradient. Therefore, our over factor is lambda over 2 pi epsilon 0. The factor of 2 cancels because of this even function. The integrand is an even function. And then this is the general form of the electric field. Here I did not make use of this complicated derivation for the sine hyperbolic function. Okay, you could have used this table, but it is stupid. We have a very simple theorem to find the answer directly. And then you take the limit L goes to infinity. If L goes to infinity, this contribution vanishes. So this is the electric field due to a uniform charge distribution along a straight wire. You find one dimension along the z-axis is integrated out. Now the inverse square law integrated out to find the two-dimensional version that has 1 over rho dependence, because circle of radius rho is 2 pi rho. So this is 2 pi rho epsilon 0. In case we have a three-dimensional case, that is a spherical charge, spherical form, a point charge generates electric field, then the area of the surface is in the three dimension. This area is a 4 pi rho r squared, and we have epsilon 0. So this different structure appears in the due to the symmetry of the Euclidean space.